Now let's look at one final problem from this chapter, which involves multiple particles. So this is a relative motion analysis problem. And this is again a kind of block and tackle system. You can see that we have three pulleys over here and we have two blocks, which we're calling P and Q. One thing you would notice over here is that we have actually two cables, right? We don't have just one. We have one that goes from A to B to C and ends at D, and the other cable that starts at G, goes to H, I, J, and then wraps around and comes down like this, right? So essentially we have two cables to deal with, and each of those cables will be assumed to be inextensible. So they won't stretch, they won't contract, okay, as P and Q are moving. The other thing you would notice is that the point E could move up and down, right? Point N, of course, is not going to be moving up and down, but the point D could move up and down as well. Okay, all right. So that's not that's obvious in this case. So how do we solve this problem? Well, let's first read the question. So the figure shows the pulley system for which we want to determine how the velocity and acceleration of block P are related to velocity and acceleration of block Q when they're connected by pulleys and inextensible cord shown. Find the equations relating VP to VQ and AP to AQ. So the procedure to solve these problems is to first identify the coordinate system. Both P and Q are going to be moving up and down only. They're doing what we call rectilinear or straight line motions. So choice of a coordinate system is obvious. We will go with the Cartesian coordinate system. So Cartesian coordinate system, we have to pick the origin. So we'll pick our origin to be, let's say, right at the ceiling, and we will indicate our position variables. In fact, in this case, the position variable is shown as YP, and I'll just write it a little bit bigger, YP and YQ. Okay. Those are the position variables for P and Q. So let's just start with the left cable that goes from A to B to C and ends at D. That's one cable. We'll call it length L1. The other cable goes from G to H to I to J to K to L, and we'll call it L2, okay? And L2 would also indicate the length of this cable. So the constraints over here are that as P and Q move up and down, the lengths of the cable don't change. So if we can write the length L1 and L2 in terms of these position variables shown over here, then maybe we can solve for the velocity relationship and acceleration relationship. So let's start with L1. So what is the length? What is the length of the cable segment AB? Okay, so we're looking at segment AB. The segment AB can be written as YP minus EF, right? So that would be YP minus EF, and I'm going to ignore the EF because EF is actually constant, plus this part, which is also constant, so I will ignore that, plus this part, which is CD. So what is CD? So CD is actually nothing but YP minus EF minus distance from here to here, right? But is this distance going from G to H? Is fixed? It's not, because the pulley is moving up and down. So what I'm going to do is I'm going to introduce one more position variable, and I'll call it Y sub D. Okay, I'll call it Y sub D. That indicates the position of point D. So what we got is YP plus YP minus YD, right? YP minus YD indicates the length of CD, segment CD, and that is equal to constant, right? Whatever it might be. So we get 2YP minus YD equal to constant. So if I take the delta on both sides, what do we get? I get 2 delta YP minus delta YD equal to delta constant is always 0, right? If I differentiate it, I get 2 VP minus VD equal to 0. I differentiate once more, I get this. Okay, so I have these two relationship for velocity and acceleration, but velocity of an acceleration of point D is not something that we want, right? What we're looking for is the velocity and acceleration of point Q. Okay, so let's now look at the other cable, which goes from G to H. That wraps around, goes up, wraps around, and comes down, right? So what is the segment length? GH. GH is nothing but YD. So that is YD plus wrapping around the pulley. That's not important. So we have again now YD minus MN. So this is not important. So this is JI plus we have KL. So KL is nothing but YQ minus MN, which is a constant, and that is another constant, right? So we get basically 2yd plus yq equal to constant. So if I apply delta, I get 2 delta yd plus delta yq equal to 0. If I differentiate it, I get 2 velocity of d plus velocity of q equal to 0, and differentiate once more, I get that. So let's call this 3 and 4. Okay, so from 1, 2, 3, and 4, 1, 2, 3, and 4, I can get rid of the velocity of d because we don't need that, right? So let's do that. So velocity of the d from 3 is equal to minus vq over 2. So I'm going to substitute this into 1. So I'm going to take this and put this into 1. What do I get? 2vp minus plus becomes plus vq over 2. So I get 4vp plus vq equal to 0. And I'll have the similar relationship for acceleration also. Okay, so I get that. And that's what we're looking for. So what this is saying is that if let's say the particle P goes down by a certain amount, then the Q is going to go up by 4 times that amount, right? So P comes down by, let's say, 1 inch, then Q is going to go up by 4 inches. Now, this is the kind of problem which may not be that straightforward to solve by just looking at the picture and trying to figure out by how much distance P and Q are going to move with respect to each other. Okay, maybe in some cases you'll be able to see that. In fact, in this particular problem, maybe you can still see it because you can see that if point E goes up by 1 inch, it will free up 2 inches of the cable on the both sides, and that 2 inches further will move D up, right, by 2 inches. So you'll have 2 inches and 2 inches freeing up over here, and that'll give you 4 inches by which Q can actually come down, right? But if I give even more pulleys and more blocks, this will become even more complicated.